మా నాయుడు గారు మాట్లాడుతున్నారు.
నాయుడు గారు, అరే నీకు గుర్తుపట్టలేదు, మాస్క్ లో మనం గుర్తుపట్టట్లేదు.
నాయుడు గారు మా హెడ్.
ఓకే, బాగున్నారా? యా, ఐ నో, కంగ్రాచులేషన్స్. ఐ నో యు ఆర్ ద హెడ్ ఆఫ్ ద డిపార్ట్మెంట్. గుడ్ గుడ్. సో ఎక్కడ వీళ్ళంతా అంటే ఆన్లైన్ లోనే అటెండ్ అవుతున్నారు కదా అందరూ?
ఆన్లైన్, బికాస్ ఆఫ్ కోవిడ్ ఆన్లైన్.
I know. Yeah. Nobody is in the, of course, it's not possible. Yeah. So 1 hour presentation, 15 minutes discussion.
Ante. Yeah.
Okay. Perfect. We will wait for some time if you want. We will wait.
Yeah. Inka 2 minutes undi.
No problem. I have no issue. ఎంతమంది ఉన్నారు? ఎవరు లేరంటున్నారు, ఇంకా ఎవరు లేరు, రాలేదు. I think you are muted.
Because some research scholars are there in the halls. Okay, they are listening to the lecture here.
Okay.
And some students are also there in their respective rooms. Okay. We have arranged there.
Okay.
But directly online YouTube listening may be less, because from today onwards the college has reopened for contact classes.
Okay.
Yeah.
Okay. So then where are those research scholars?
Research scholars.
Okay. They all have this one, or they are listening just like that? Okay.
No, they are just listening, and the screen out arrange chesam ikkada peddadi. They are listening and the speakers are there. Okay.
Okay.
So good afternoon, ladies and gentlemen. I welcome you all to the second week program of a web series being organized at the Department of Meteorology and Oceanography. Today we have an illustrious speaker, Professor A.D. Rao from the Indian Institute of Technology, Center for Atmospheric Sciences, New Delhi. To introduce the speaker, I'm much privileged. Dr. A.D. Rao received his MSc degree in Applied Mathematics from Andhra University in 1978 and a PhD degree from the Indian Institute of Technology, Delhi in the year 1982. He went for his postdoctoral work on numerical storms, such prediction in India, to England, and then he joined the faculty of the Center for Atmospheric Sciences at IIT Delhi in 1982. He has been holding the position of a professor since the year 2002, and his research interests are in the development of numerical models for ocean state prediction system along the Indian coast. This includes storm surges, wind waves, Indian Ocean circulation, coastal ocean process, and internal waves. Dr. Rao has made a significant contribution to these fields, which are widely recognized. He has published more than 200 research papers in various national and international journals of repute. He is an elected member of the National Academy of Sciences, Allahabad, and he is a visiting research fellow at the University of Reading during the years 1983-84. He was a visiting scientist during 1991 at the University of Reading, UK, and the Florida State University, USA, during the years 1997-98. Dr. Rao has so far guided 18 PhD students and is very actively involved in several consultancy and sponsored research of national importance. He is an associate editor for the International Journal of Ocean Climate Systems, and he has been invited many times as a guest editor of the journal Natural Hazards Marine Geodesy to bring out special issues on the topics which are relevant to his field. With this a few words, I now welcome Professor A.D. Rao to give his lecture.
Thank you, Professor Ramakrishna, for giving an opportunity this one, and I thank Naidu Garu also for giving me an opportunity to present my talk here on this occasion. I would like to share my presentation. First, let me share. I think desktop, okay, and then let me see where it is my talk. Can you see my this one?
Yeah, sure.
Okay. Yes, okay, thank you. Okay, good. Good afternoon to all the participants. Today I'm speaking on tropical cyclones and the causes of tropical cyclone along the coast. Okay, mainly that's my focus here. And you all know that our Indian coast experience many tropical cyclone every year. And of course, there are some pockets along the coast which are more prone to tropical cyclones. So I would like to emphasize not on the tropical cyclones, causes of tropical cyclones. That means how much sea level rises due to the passage of a tropical cyclone, and also how much it translates into coastal inundation. That's the most important parameter which everybody would like to know whenever there is an approach of cyclone along the, towards the coast. So that's my focus of the topic. Before that, I just for completeness, I would like to say something about tropical cyclones. What is a tropical cyclones? Being it's a, for the students, for the benefit of the students, I would like to give basics also at the same time, not too much technical also. A tropical cyclone can be considered as a large vortex, atmospheric vortex, and extending from 100 to 1200 kilometers with spiraling winds around the central low pressure area. In the northern hemisphere, the winds rotate around the cyclone in an anti-clockwise direction, and in the southern hemisphere in the clockwise direction. That's the general rotation of the cyclonic winds. And this is the cyclone which you can see from a satellite. Okay, at the center you can see that there is a hole that is the eye of the center actually. Okay, there actually you don't find usually this eye of the center is very calm winds without much rain and surrounded by strong convective clouds, and it gives a lot of precipitation in the area. Being it's dynamic, the center of the cyclone moves as the cyclone approaches towards the coast. Okay, if you look at the vertical structure of a cyclone, eye is there in the around 10 to 15 kilometers. It's a clear eye, you can see as seen from the satellite also. And after the eye of the cyclone, you have very strong winds associated and causing a lot of precipitation and so many things happen. But this is the distribution of the pressure and wind speed across the cyclone. Okay, then what happens when a cyclone approaches towards the coast is that it raises the sea level near the coast. Okay, so that is called storm surge. Okay, what is a storm surge? It's a definition. We can always say that it is an abnormal rise of sea level caused by a cyclone moving over a continental shelf. I hope you all know about what is continental. I will come back to that slide also. The storm surge is the most destructive element associated with any tropical cyclone. Most of the human disasters caused by a tropical cyclone has been attributed to storm surges. That's very important. Okay, that's why we are actually studying what is storm surge associated with the tropical cyclones. Okay, but just to get the fundamentals, there are only two types of waves, either in the oceans or atmosphere. What are those waves? Transverse waves and longitudinal waves. You all know that one. I don't want to define what is transverse. But in the transverse waves, there are again two types of waves. One is vertical transverse waves and another one is horizontal transverse waves. Okay, horizontal transverse waves are not actually, doesn't cause much damage, but vertical transverse waves are most dangerous. And storm surges comes under this category. Okay, so what are the factors responsible for generation of storm surges? It's the most important actually. Intensity of the cyclone. That means if the cyclone is more intense, then you expect that more surge or storm surge will be generated. Okay, and shallow bathymetry. If the deep waters, in the deep waters you don't get much surge, but in the shallow waters, you get more surges. And continental shelf width. I will come back to what is continental shelf width. This is also a place. This also plays an important role for the generation or amplification of storm surges. Okay. Next one is coastline geometry and shape of the basin. This is very important because Bay of Bengal, if you consider it is like a funneling shape of the basin. That means as you go from south to north, it's a converging. That means the width of the basin is reducing. So that means any system which develops in this system, the energy gets trapped in this one. That's why the shape of the basin is also very important. Then approach angle of the tropical cyclone, in which direction it is coming. That's very important. Okay. And shape of the basin I already described. Okay. Factors responsible for total water elevation. Okay. Storm surge is only one parameter which raises the water level at the coast or sea level rise. But there are so many other things which will also contribute on the total water elevation near the coast. What is that one? In addition to storms such as astronomical tides. Okay, tide also actually brings more water actually near the coast. So therefore, that will also play an important role on the total water. And also wind waves. These are short waves. These short waves also contribute to some extent on the total water elevation. Therefore, the combined effect of short waves, long waves, and tides and storm surges are considered comes under category of long waves, and wind waves come under short waves. So therefore, these two waves actually how they interact each other is a very important scientific problem to understand to understand the total water elevation near the coast. Okay, factors responsible for coastal inundation. What is ultimately the water piled up at the coast will be inundated the low-lying areas. That's the most important crucial parameter for the for the coastal population to know. Otherwise, there is no just saying that the storm surge comes 2 to 3 meters or 4 to 5 meters. That's not the issue for the coastal population. What is ultimately translating into coastal inundation, so that whether they should be evacuated or not. Okay, because that's most important for the forecasting purpose. Therefore, local land topography also plays an important role. If there is a river system nearby, then also it causes more inundation. So these are the issues related to coastal inundation. The next one is that I'm just showing how the cyclonic wind distribution. If you divide the cyclone into 4 quadrants, okay, and at the time of landfall, this is the wind system, assuming that it is a symmetric. Usually cyclone is not symmetric, but I am just showing for showing to you, I assume that it is a symmetric cyclone. That means on the right side, this is the track of the cyclone. The line which I am showing is the track of the cyclone. On the right hand side, the winds are directed towards the coast. These are called onshore winds. On the left hand side of the track, you have the winds directed away from the coast. These are called offshore winds. Okay, but the winds which are actually on the onshore winds, okay, bring more water from the deep water to the shallow water. That's why at the coast the sea level rises. Okay, but what happens on the left side? The left side, the water is taken away from the coast. That means the beach is exposed. This is also equally important because no ship should be anchored on the left side of the track. Okay, equally important because otherwise it will be grounded. Therefore, this is called the water level decreases here, the water level increases on the right side. Okay, these are the issues which I'm just showing. So I'm talking about the storm surges on the right side of the track only. This is the typical bottom topography of the ocean. Okay, if you look at the typical bottom topography, then you can see that the slope of the depth, is very gentle here up to some distance, and after that the depth decreases suddenly. Okay, the depth decreases suddenly. That you call it actually shelf break. Okay, so from shelf break to the coast is called continental shelf. Okay, whenever there is a storm surge wave, that I call it actually long wave, propagates from the deep water to the shallow water, it travels on the continental shelf. Okay, any long wave propagates in the continental shelf, the wavelength decreases, the wave height increases. That is the property of the long wave. Okay, therefore, how long actually this long wave propagates on the continental shelf is the most important thing. If you have more continental shelf width, that means you expect that the wave height increases significantly. That's very important. That's why I said continental shelf width also plays an important role on the amplification of the storm surge. Okay, if you look at the continental shelf for the west coast, it increases from 30 kilometers from south of Kerala to north of Maharashtra, about 330 kilometers. So you expect that how the amplification takes place actually from these just because of the width of the continental shelf. Similarly, on the east coast also, the continental shelf width increases from south to north, particularly in the West Bengal region. You have very long shelf width. That means any cyclone approaches in this region may cause higher amplitude of storm surges. Right. So now I'm just showing the storm surge. But now another important aspect which you have to consider for the rise of the sea level is due to tide. Tide, you all know that those who are living in the coastal region, they are very familiar about tides. Tide is a very regular phenomena. That means you have a rise and fall of the sea level is seen every day. If it is a semi-diurnal tide, you see two highs and two lows. If it is a diurnal tide, you will see one high and one low. It's like depends upon the type of tide. You have tide every time. Okay, every day you have tide. Therefore, suppose a cyclone approaches at the time of high tide, you expect that the total water raise at the coast will be high compared to the normal low tide time. Therefore, you have to see the tidal conditions also. At what time the cyclone is approaching at the coast or striking the coast or crossing the coast. Okay, suppose you have 2 feet tide here, and on the top of it, the cyclone generates 15 feet surge, then the total amplitude of the wave is about 17 feet. So therefore, tide is also contributing on the total water elevation. That's the most fundamental thing which you have to understand. Right? So where it is crossing, is it crossing at the, whether the cyclone is crossing at the highly elevated area like Visakhapatnam or low-lying areas like Machilipatnam area. Okay, it all depends. The same intensity of cyclone hits at different configuration of the topography, then the consequences are different. You expect that if it is elevated area, then inundation may not be there, but wind damage will be there. But in the low-lying areas like Machilipatnam, you have both inundation as well as wind damage. So therefore, it all depends where it is actually crossing the cyclone. That's very important. Another important thing, wherever it crosses, okay, the elevation at the coast piles up, and that piling water, penetrates or propagates over the land depending upon the local topography. And that is the most crucial part for the forecast of the storm surges and associated inundation, because so that you can evacuate those areas where you get very high water levels of inundation. Okay, so therefore, for forecasting purpose, not only storm surge height is important, not only the storm tide height is important, what is its implication on the inundation? That's the most important thing. For that, you need separate kind of models to include or to compute rather coastal inundation. I will come into that discussion latter part of my talk. Okay, so this is a general. You all know that the cyclones happen, in a year in 2 seasons. One is pre-monsoon season and post-monsoon season, either it is for Bay of Bengal or Arabian Sea. Okay, and we all know that actually which are the pockets all along the coast may not be very important for the are not actually prone to the cyclones, but some pockets of the along the east coast and the west coast, particularly on the west coast Gujarat, and the east coast actually most of the places along the coast are actually prone to the cyclones. Therefore, you have to see actually where you have to concentrate for your forecast and all. Okay, so based on the information of tropical cyclones for the last so many years from India Meteorological Department, if you calculate actually return period for different time periods, 10 years, 50 years, 100 years, for each maritime state, you can see that along the west coast, Gujarat is the highest pressure drop. If the pressure drop is high, you expect that the intensity of the cyclone is also high. And Gujarat is actually most vulnerable for tropical cyclones, and Kerala is the least. Similarly, if you come to east coast of India, all the maritime states, West Bengal, Odisha, Andhra Pradesh, Tamil Nadu are important, but more significantly, Odisha plays a prominent role. And tides, actually, as I said, you have a if tides can be measured from the tide gauge. I don't want to go into the details, but what kind of tides you have, whether it is semi-diurnal or diurnal tides, it all depends actually. Okay, so I don't want to. At some places you may have mixed tides also, but it depends upon the region. Okay, I don't want to go into the details of the tides, but tides can be measured and predicted very well. Okay, by the numerical models or by any way. So you can always predict tides much in advance. That's not an issue. Even after 100 years, what is the tide on so and so date and so and so time? It's very easy to, because the forcing is very, very known. Okay, because the tides are caused by the astronomical astronomical bodies, attraction between the astronomical bodies, celestial bodies. Okay, therefore it's all known. We know the movements of the all the astronomical planets. So using Newton's gravitational law, we can easily find out what is the force. Therefore, you can find out what are the elevations from the attraction of these celestial bodies. Okay, so why I am saying that one? So for inundation purpose, you need to include in the models the tide also. Therefore, we all actually take high tidal simulations also. First, we simulate tides and see that our models are actually perfectly working for the simulation of tides. Unless the models are simulating tides, you cannot actually use it for storm surges also, because tide and surge, gives actually a different kind of water levels at the coast. Therefore, you have to consider all the time tides into account. Okay, tide plus surge interaction, though it's not a linear one, but it's a non-linear one, but still at what phase is also important, amplitude is also important. Okay, both are important for the interaction. Okay, so for that purpose, our models are validated at all the tidal gauges, tide gauge stations. So this is actually, I'm just showing actually at Paradeep and Ennore. This is actually for Oka and JNPT, means it is Bombay. So we have validated for East Coast and West Coast. So therefore, I can use this model for the storm surge prediction also. Okay, so usually the tide increases from south to north. Both along the east coast and also along the west coast. Particularly in the Gulf of Khambat, the tidal range reaches up to 12 meters. So therefore, you can see how important it is actually to include in the tide surge interaction. Okay, so at some pockets the tidal range is very, very high, particularly in the Bay of Bengal. Actually, at the headway region, the tidal range is about 4 meters. So therefore, you have to consider the tide into account for calculating the storm tides. Okay, so if you look at the grid, actually, I'm just explaining how the models are being developed. This is actually finite element models which we use, and we have developed these models with variable grid, structured grids. And I don't want to go into the details actually how this one, but the resolution varies from the coast to the deep waters. Okay, for 100 meters to actually 20 kilometers or 50 kilometers range. So therefore, this is the typical grid generation of the models. And I'm just going to explain how the inundation model, okay, is being actually used actually or developed. Okay, so I'm just showing for a zoomed portion of the grid. This yellow line is the coastline. The yellow line is the coastline, and right side of the yellow line is actually ocean. Left side of the yellow line is coast. That is the land. Okay. Whenever the storm crosses the coast here, okay, you all know that the surge or storm tides happen on the right side of the track. Okay, that water actually penetrates on the land. So therefore, you have to consider the land also for in your model. Otherwise, how do you get inundation? Therefore, we have included the topography up to 10 meters, okay, on the landward side, so that I can include any kind of inundation. Okay, why, you can ask actually why I have taken 10 meters topography, assuming that we don't get more than 10 meters surge or storm tide. Therefore, on that basis, we have limited our boundary on the landward side up to 10 meters. Okay, and the resolution varies from the coast. We always take high resolutions near the coast because we are more interested actually near the coast rather in the deep waters. Okay, so if you zoom it, actually the grid looks like this. This green line, the blue line is actually coastline. Initially, when there is no cyclone, okay, when the cyclone comes here, okay, so these elements, we call it element actually, okay, these elements, triangular elements, are filled with water. Initially, it is dry, but later it will become wet. Okay, and the seaside is always wet, so therefore the model is integrated whenever it is a wet grid. Okay, this looks like this. Okay, this blue portion is the sea and this white portion is land. Okay, before the cyclone crosses, actually all the elements on the landward side is dry, but when the cyclone approaches, slowly these elements get wet. So we use actually dry and wet schemes. I don't want to go into the detail, but I have got animation, but I don't want to show the animation here. But what will happen after the cyclone crosses? So these white portions, that means dry land area, has become wet, and you can see how much water levels are piled up here, actually 4 meters and all. This is from the above the mean sea level. So people don't understand what is mean sea level on the land. So the public doesn't know actually what is mean sea level there, where he stands. Therefore, what I do actually, I subtract the local topography mean sea level from the mean sea level. Then I calculate what is the depth of the water inundation. Okay, this is the depth of the inundation. Okay, you can see that the depth of the inundation is about maximum water levels are 2.6 meters near the coast, and the extent we can see up to 3 kilometers. This is what is precisely required whenever there is a cyclone approaching towards the coast. Okay, so you can see that what are the areas which are likely to be evacuated, what are the depths which are more important. Okay, you can see the water depth, so that using that water depths, you can see that which are the pockets which are more vulnerable for the evacuation purpose and all. Okay, so this is the ultimate thing which has to be done for any cyclone approaching towards the coast. That is our objective, what I am doing actually for the last so many decades. Okay, we are trying to improve actually. Inundation is not a easy thing because there are so many things which are actually involved in the calculation of the inundation, which I will come in the next few slides. Okay, but ultimately this is a societal impact. The study is actually related to the societal impact. This is the most important work which is to be directly applicable to the society. Okay, so that it can be benefited. We use actually for the we give actually forecast for IMD whenever there is a cyclone, even the recent cyclones also last 2 weeks. So we have been running our models and providing the information to India Meteorological Department. Okay, that is our whenever there is a cyclone, that is what we do actually on a real-time basis. Okay, so what are the issues related to the inundation? That is my objective of the presentation. Okay, the most important thing is for inundation is how best you represented the local topography or onshore topography. Okay, if you have more, depth is not a problem. Ocean depth we can always get actually more accurately by different observations. Okay, but the most important thing is onshore topography. Onshore topography, you have so many satellite data, okay, Cartosat data, ALTM data, SRTM data, but each data set has got limitations, okay, on resolutions as well as no extent of data availability. Okay, but we all merge all these data, whatever is the best we take for that. And if you don't consider all the data, there are so many issues. For example, I will show you in the next slide probably. Yeah, this slide is suppose if you want to represent the Chilika Lake, okay, if you don't use proper data, for example, ALTM data is the best for the Chilika Lake because it gives the proper water depths actually of Chilika. Okay, but if you use SRTM data and all, they don't give even whether there exists a Chilika Lake or not. So therefore, you have to be very careful. What type of data is it representing the ground truth? That is the most crucial thing which you have to see whenever you're talking about inundation. Okay, so the importance of onshore topography and also resolution. Cartosat data has got different resolution, both horizontal and vertical. Horizontal is very good. Our satellites give very good horizontal resolutions. But the problem with the vertical, for storm surge heights and water depths, you need vertical resolutions are also very important. Okay, I'm just giving an example for a funny cyclone which struck actually in the last year, 2019 May. You all know that the cyclone hits near Puri, and this is the most very fastest cyclone and the longest cyclone. It is traveling about 3,000 kilometers and with a 14.6 kilometers average speed. So, and it is very severe cyclone actually. Of course, it's not super cyclone, but after probably after which cyclone is that actually? Violent cyclone. After violent cyclone, I think Fani is the most strongest for this region. Okay, so therefore, I would like to show you some of the results for this one. Okay, this is using the best track. We are computing actually coastal inundation. Okay, so if you look at how much inundation is taking place actually in the Chilika region. Okay, this is the inundation, coastal inundation, which is also actually observed because we got the ground truth data later after the cyclone crossed. We got the inundation in this region, and we have checked actually our simulated water level elevations also with the tide gauge data. So it's very well simulated. So these are the issues which you have to. Inundation is a very tricky business because we don't get much data on the inundation, but we always get storm surges. Storm surge is not an issue, but inundation validation is a problem. Therefore, we have to see in different ways actually to find out how best we can validate the inundation. Inundation has got two components. One is the extent of the inundation and what is the water level depths. That is also most important. So both the things it's very crucial to validate. Okay, another important component for the inundation is that LULC data, land use land cover data, because this is the most important thing for the propagation of the water over the land. Okay, if you have vegetation, what kind of vegetation you have, whether you have mangroves in this region, whether you have is it agriculture land, what kind of land it is, depends on that your water levels or propagation of water over the land depends. Therefore, I use actually LULC also to consider for computing coastal inundation. So you will see the difference. Without LULC, you have a kind of this type of this one, and if you use LULC, you have a different kind of inundation. So it all makes difference actually. So which is correct? That is the most important. It's very difficult actually to say at this moment, but it is very important in future to see that how LULC inclusion, gives better computation of inundation. That is yet to be seen. But you find a lot of differences with LULC and without LULC. That means it is really play into picture. Friction makes difference. Therefore, the propagation of water over the land makes difference. This is the main issue actually, again, a research area. Okay, similarly, if you consider without LULC, you have more inundation in this region, Hooghly region, which is not seen actually. We confirmed from the India Meteorological Department that if you use LULC, you have less inundation. So that is probably cyclones and which causes more inundation, and how much area in terms of kilometers, square kilometers, which I want to actually show you some of our studies. So for this, I consider synthetic tracks. Synthetic tracks represent the most probable direction of the cyclones which happen there. Okay, so I constructed district-wise all synthetic cyclone tracks. Okay, based on the last few decades cyclone tracks information. I'm just showing only for East Coast. Similarly, the study is also made for the West Coast. Based on our study, I would like to show you along the East Coast, there are so many river systems which are also very important actually to consider these river systems. So in our model, we consider these river systems. For example, Krishna, Godavari, Mahanadi is a big basin compared to Krishna and Godavari, and we have Hooghly is another complicated river system. Okay, so this is all considered in our models, and we computed using these synthetic tracks what is the most probable extreme water elevations that do occur along the coasts of all the maritime states. Okay, so if you look at for the entire Odisha, okay, so I'm just zooming this portion here in Odisha. This region actually is more vulnerable from Dhamra to Balasore, this area. Okay, it all depends actually. Coastline geometry also plays an important, because this is a concave type of coast, so therefore energy gets trapped. That's why you get more water levels, and hence you get more inundation. So I have given actually detailed inundation mapping for the entire East Coast and West Coast. Okay, these actually are very useful for any coastal planning. Okay, development of any coastal structures or anything. And also you will see that what are the depths associated with this inundation also, so that you will get a complete mapping of vulnerability maps for the entire coastline. But I am showing very in a very coarse resolution, but I have computed for every 10 kilometers along the coast. So that's very detailed maps. You can see where are which are the, for example, Tamil Nadu, you think that it is safe, but Ramananthapuram, actually the area is very vulnerable area. For example, in our region, Andhra Pradesh, for example, Krishna Godavari basin is the most vulnerable region. Similarly, Mahanadi basin is the most, and Hooghly region. These are the pockets where you expect more inundation because of the basin. That's why you have to treat the river basins separately. I will come to the that point also at the end of my talk. Okay, so these are the I'm showing actually district wise. What are the elevations that generate for a particular district, and how much it is translated in terms of water depths over the land. So the left hand side actually gives the elevation. Here the actually depths, actually water depths. That means inundation. Okay, so it's more the depth, it's more danger. Okay, and another third. This picture is the district-wise inundated area. Okay, we calculated in square kilometers. Okay, you can see Medinapur and 24 Parganas, they have the highest inundated area because it's a really most low-lying area. Okay, and before that you have Odisha also is very highly inundated area. So you can see that how much area is getting inundated. The last histogram shows, okay, we have categorized into three areas, okay, three parts actually. One is water depths, okay, area less than 1 meter, and area with 1 meter to 2 meters, and area more than 2 meters. Anything more than 2 meters is dangerous because no human being can survive there. That's why we put it in red zone. So you can see that Odisha is the most vulnerable that way actually. Okay, the more red areas. That means the water depths associated are more than 2 meters. Okay, if it is less than 1 meter, it's not that much severe. Okay, so still people can live safely with the 1 meter depths. Okay, but if it is 1 to 2 meters or more than 2 meters, most vulnerable, people have to be evacuated from this region. That's why we are showing actually just for making the difference what type of water depths you get in a particular district. Okay, so another important aspect which I am trying to put this one is river actually. Okay, actually for a river you can't use just a hydrodynamic model, because so far we have been using hydrodynamic models for computing the storm surges and inundation. But recently we have included hydraulic models, coupled hydraulic models. What is the advantage of these hydraulic models is that you all know that during the cyclone time, lot of precipitation occurs. Okay, whenever you consider inundation, inundation can happen many ways. One is that, of course, whenever there is a storm tide penetrates over the land, you get actually an inundation. That's what I have shown so far. Okay, but inundation can be caused by other two parameters also. In addition to this, one is precipitation. Okay, you experience a lot of precipitation during the cyclonic time. Okay, you have to take into account of the precipitation also. Okay, and also if you have so many river systems there, then you have a freshwater discharge or river discharge from the upstream end. Okay, so that also brings a lot of river discharge, and over the region basin, river basin, you have precipitation, and from the ocean side you have storm tide. Okay, all these effects will be causing actually inundation. Okay, therefore in the recent our studies which is coming in JJR, we have to take a coupled system which includes precipitation and river discharge from the upstream, in addition to storm tide effect. Okay, therefore that's what is being done in this study. Okay, so I'm just showing for Mahanadi Basin. Mahanadi Basin, why I selected compared to Godavari and this one, this is most complicated in terms of more tributaries. Okay, it has got more tributaries. So that means, the area of the basin is much larger compared to any other basin. Okay, river basin. So therefore, I took this one as a a pilot project, and we have done actually, and we could be able to do a lot of good work in this area of how do you represent inundation in this region. That's the focus. Okay. So, and also we considered LULC also. That's very interesting. So you have taken all possible parameters which influence the inundation. Okay, so again, how do you represent river tributaries? That's a classical problem. It's a classical problem because no onshore data will provide either SRTM or Cartosat data or ALTM data. No data will provide actually your representation of the tributaries properly. Therefore, you have to do some kind of, manually also, okay, knowing the cross section of the Mahanadi Basin. Okay, so I got the river basin characteristics. Different maps are there, hydrological maps. So using that one, we have to represent, and that means you have to modify the SRTM data and put it again modified SRTM in our model. Okay, that's what we did. If you use actually modified SRTM, that what it looks like this, your channels are better represented here. But if you use straight away SRTM, it looks like this. So that means channels are not actually clearly represented. Okay, therefore you have to do, I don't want to go into the details actually how that we modified the data. That's it, that itself is a cumbersome. I don't want to go into the details, but that is what is required. Okay, so here actually two cyclones are considered. One is actually 1999 super cyclone. You all remember this is the most strongest cyclone which ever crossed actually in our east coast or west coast. Therefore, this here actually the pressure drop is 98 millibar. That was the highest recorded for our region. 1999 super cyclone. This is exactly crossing actually the river basin. It is almost crossing across the river basin. And another cyclone, Phylline cyclone in 2013, it is crossing south of that river basin. So I have taken these two examples for displaying our results, but I don't want to go into the details of each this one. What it essentially show that actually how this our coupled models, okay, are better simulated for inundation. That's the most crucial thing. Okay, but how do you validate? That's the question. For 1999, we didn't have any data for the inundation. But for Phylline cyclone, we got some satellite data. Okay, of course, it has its own limitations, but we have used actually satellite data to validate that one. So that way we have seen actually. Okay, so we have seen actually inundation, but I don't want to go into the details whether if you use modified SRTM and unmodified SRTM, it makes a lot of difference. That what it shows actually for river systems are to be accurately represented. That's what it makes difference. How much it is making the difference in terms of square kilometers of inundated area. We all have actually seen those things. Okay, so this is for 1999 cyclone. So how much area is got inundated with and without river discharge? Again, we have seen that river discharge is also known actually. I think in the previous slide, somewhere I put it, we have the river discharge calculations, okay, from the upstream. We have taken exact river discharge from the upstream end, and we have incorporated in the model and see that how much it brings extra inundation. All these things are actually made some studies. Okay. This is also again for 1999. We validated with the tide gauge data also in this 1999 super cyclone. Coming to 2013 Phylline cyclone, but this cyclone actually crossed the south of this river basin, but still, a lot of precipitation occurred in this one during this period. Okay, and also the winds are very strong. That has led to some storm tides here also. Okay, therefore there is some kind of inundation here for 2013 cyclone. Phylline cyclone. Therefore, we compared again our tide gauge data. It is very well matching. And again, I would like to see you with the how much river discharge. We have the river discharge day-wise also. We have taken the river discharge 9th October, 10th October, how much river discharge. All the precipitation, sorry, this is the precipitation, and similarly river discharges are also taken into account in this one. And finally, we compared actually with satellite picture. Okay, you can see that this is the one which LULC with LULC. Okay, and the river discharge plus precipitation is compared with the satellite data. Okay, you can see that there is a good match with the circled one. Okay, so you are getting exactly at the right place with the satellite data. Okay, so that means our models are actually, when you represent LULC data and river discharge, precipitation and storm tide, if you include all these things, then if you we compared when compared to satellite data, the pockets which are shown in the satellite is really matching with our computations. So that's why we are a little bit confident about this coupled system. It is giving better estimates of coastal inundation. So therefore, this is the important thing which recently we have incorporated precipitation. This is the first time actually in India across in many places actually the precipitation is taken into account. That's river discharge is taken into account earlier by different authors, but precipitation is not taken into account. This is really a challenging research area which we have to further improve. Actually, this is one of the drawback of this one is that we have used actually area wise, the entire area has got the same amount of rain. It is not so actually. So that is one thing. The entire basin has got the same amount of precipitation. This may not be true, but what to do? We don't have that pocket wise actually in rainfall. So therefore we have to take for the entire this one. But however, whatever it is, with this little drawbacks, still we could achieve the satellite comparison very well validated. Only thing is we don't know, obviously the satellite picture doesn't give the depth of the inundation, but our model gives depth of the inundation also, but we cannot validate unless we have a in situ observations. So how do you get in situ observations is a question. Okay, so these are many studies which are done, which I don't want to go into the details of this one. Similarly, for 1919 cyclone, we have made so many simulations and well compared with LULC and without LULC. It makes a lot of difference and all those things. At the end, what I would like to focus is that what is required for the public. Okay, is required. You need an integrated prediction system, location-wise, location-specific integrated prediction system for assessment of cyclonic risk and vulnerability. This is the title I chose because this is the most important parameter for the public point of view. Okay, scientific point of view is different, but for public point of view, if you can assess cyclonic risk and vulnerability, so that you can take actually appropriate measures for any kind of eventuality. Okay, but for this, what do you require? Technically, okay, you need actually a good atmospheric model, okay, mesoscale atmospheric model. So far, no mesoscale model, atmospheric model gives actually very accurate, I'm telling you, very accurate prediction of the track and its intensity. Okay, why I am saying that one? Of course, there are improvements for so many years. There are improvements. We are getting better forecast of the track and all these things. But for storm surges, okay, we need accuracy in a different level. Okay, we need actually accuracy of 1 kilometer. Because inundation levels differ actually. If you take actually 10 kilometers error or 20 kilometers error, 30 kilometers error is not possible with the storm surge models. Because instead of evacuating one village, you will evacuate some other village. Okay, if you use the same track. Therefore, our accuracy of the cyclone track should be as accurate as of less than 1 kilometer. That is the kind of accuracy which we expect from the atmospheric model. Okay, we expect. If it is achieved, then you can use directly the atmospheric model coupled to the ocean model and calculate storm tides. Okay, and how much rise of water level at the coast. That's a very good ideal situation. In the absence of this one, what we are doing is that we are using an empirical wind models by taking into account of the pressure drop, radius of maximum, representing the cyclonic distribution of a particular cyclone. Okay, so I calculated all these things using wind modules, cyclonic modules. Very famous modules are there. We have also modified those modules using our own data. Okay, so this is required actually. You need a coupled atmosphere and ocean system to compute storm tides. And another important thing is that storm tides using coupled system to consider the interaction with the wind waves. I have not covered today wind waves. Wind waves are actually short waves. Okay, so short waves also contribute some kind of wave setup. on the top of the total water elevation. So therefore, there is about, we have made a lot of studies how much it contributes on the total water. Okay, about 15 to 20% change in the total water elevation. So this is also very important. How they interact long waves and with the short waves is a very good research problem. Okay, you have to take into account of the wind waves also, in addition to storm surges and tides. Okay, and another important thing is for the river systems, you need a separate hydraulic model. Therefore, you need a coupled system hydraulic model with the hydrodynamic models, which I showed you. It is very, very important. Whenever a cyclone approaches in the river systems, yeah, your hydrodynamic model is not sufficient enough to give the details of the coastal inundation. Therefore, you need a coupled system to compute the better computational level. I mean inundation levels. Okay, and also if you get all this information, you have to use GIS. Okay, so that you can really project on the global Earth. Okay, our models can be put it on the global Earth to see that whether a particular house is actually safe or not, for a particular street is inundated or not. So all these things can be done if you use GIS themes, so that you can identify the vulnerability of the cyclones, the affected regions. So you need a complete, an integrated system to tackle this problem. So there are many players in this one. So if you include all the players, you will get a very effective system. So what is required actually? You require very good data also to support this high resolution models and all. Okay, what are these things? You need high resolution cyclonic winds. Okay, and you need very accurate bathymetry over the continental shelf, because over the continental shelf only the height of the storm tide increases. Therefore, it's very important. Depth is very important, and also you need coastal geometry. Okay, no coastal coastline is like a straight line. It is a zigzag. So therefore, you have to take the each and every detail of the coastline geometry. And also very important for inundation is the land topography with LULC. Okay, you need to have LULC data also, latest information, what is the ground truth to get, so that if you have all this database to support your coupling system, you can actually get very good inundation. That's my talk. Thank you very much. Any further information, you can contact me, and all my publications are in the open website. You can go to my web page and see more details from this one. I have got so many publications, some such as about 50, 60 top publications. In this one, if somebody is interested, you can always go through it using my web page. Thank you very much. So, over to Professor Ramakrishna. I think you are muted. You are muted. Professor Ramakrishna, you are muted. I can't hear.
Yeah. See, one question, Devendra.
Yes, please.
It is from a student called N. Mahendra.
Yes.
Can we expect storm surge flooding along east coast of India? What kind of changes it makes over river discharge areas if we got a storm surge?
Yeah, this is what is very important actually. This I explained in my talk also. Wherever you have a river, actually, you have to consider the river discharge also. It's very, very important. Not only river discharge, you need to take precipitation during the cyclone time. That causes also inundation. So therefore, you have to have actually so many parameters which are important for the coastal inundation. That's why I explained river discharge, precipitation, storm tide, everything is important for a coastal inundation. Okay, coastal inundation is not it's not a easy thing. Okay, so you need so many parameters which are to be taken into account. It's very important. I showed you actually this importance by showing for the Mahanadi basin. Okay, it makes a lot of difference. If you don't take river discharge, it gives a different kind of inundation. If you don't take precipitation, you get a different kind of inundation. If you take only storm tides, you get less coastal inundation. So it makes a lot of difference. So if you want to have real picture, whenever there is a cyclone in the river system, river basins like Mahanadi or Krishna or Godavari or Hooghly, you need to have a complete coupled system so that you can incorporate all the information. That gives the more accurate coastal inundation mapping.
Thank you. And another question is, can we expect much disaster if the cyclone landfalls on low-lying areas like Kakinada than compared to that of Visakhapatnam?
Yes, this is what exactly happened. Hudud cyclone, for example, is the best. I was in Vizag, Professor Ramakrishna knew that one. He invited me for a talk and I gave a cyclone, on cyclones only I gave a talk. So as soon as I left that one, that on the same day, this Hudud cyclone happened. So as I told you, the intensity of the cyclone is not the matter. Where it is hitting, that's the most fundamental thing. Suppose a cyclone like Hudud is hitting in the Machilipatnam area, it would have caused actually more damage compared to at Visakhapatnam. Only for Visakhapatnam, I remembered very well for Hudud, with Hudud, only wind damage was there. Wind damage was there, but not the coastal inundation or anything, because elevation point topography is different. For example, it happens in Machilipatnam. Okay, for example, Divsema 1977 cyclone, you all know that one. Okay, it's a low-lying area. So how much coastal inundation happened during 77 cyclone and how many people died? So we all knew that one. So where it is crossing is very, very important. That's why the coastal configuration, coastal local topography, everything. There are many parameters. That's why I asked, listed all the things at the beginning. What are the parameters which are important? Okay, everything is important. You cannot just say that, okay, cyclone is causing 2 meters just based on the intensity. It's no, I never say that one, because intensity is not the only thing. Where it is crossing is the most important thing. What is the land topography in that place, where it is crossing? That's also another important. So all these parameters to be taken for actual damage,
Yeah, another question, Devendra. Why in the recent times only few cyclones are happening, that too with high intensity? Why the number has decreased sometimes while the intensity has increased?
Yeah, this is yes, you are actually, this is a climate change problem actually. Okay, in the IPCC reports, it's clearly said the intensity of the more intense cyclones, the frequency will increase. Okay, that's what actually IPCC report says. More intense cyclones, the frequency is increasing. Okay, in the recent times we have seen actually, and also in the Bay of Bengal, the number is decreasing. But in the Arabian Sea, the number is increasing. So this is a change due to climate change. Okay, so this is to be studied also. And moreover, I will tell you the heat potential in the equatorial region is increasing for the last decade, right? And that's why you are getting more number of cyclones in December. Earlier, December, we never had many cyclones in the previous decades. After a few decades before, December is a very calm, no cyclones mostly. Okay, but nowadays December is more active because of climate change. Patterns are changing because in the equatorial region you are getting more temperatures. Okay, more temperature means potential temperature is increasing in the equatorial region. That's why the number is increasing.
Yeah. Another question, Dr. Devendra. Why all the cyclones, they do not result in a storm surge? Some cyclones will produce a storm surge and some cyclones won't. What is the exact reason?
Right. Okay. For the generation of storm surges or amplification of storm surges, it depends upon the continental shelf width also, right? So where exactly it is crossing? For example, the same intensity of cyclone is crossing Kerala coast. Okay, Kerala coast doesn't have continental shelf width more. Okay, but for example, if you cross Mumbai coast, there the continental shelf width is about 330 kilometers. Okay, this storm surge is a long wave. Okay, whenever the storm surge approaches over the continental shelf width, okay, the wavelength decreases and the wave height increases because of the conservation of energy. Okay, so therefore, if the track travels more area on the continental shelf width, okay, then you expect that surge will be more. Okay, so therefore, the amplification of the generation depends. The amplification of the storm surge depends on the shelf width also. Okay, that's very important. So our coastline doesn't have the same width everywhere. It differs.
Any more questions? Yeah. Well, if there are no more questions, let us thank Dr. A.D. Rao for his very interesting and elucidating lecture. Now I request Dr. C.V. Naidu to propose a vote of thanks to the speaker.
Good evening to all. I thank all the persons who have attended the lecture entitled Modeling of Coastal Inundation in Response to a Tropical Cyclone, delivered by Professor A.D. Rao Garu, Center for Atmospheric Sciences, IIT Delhi. Professor Rao Garu is internationally reputed scientist and well known for storm surge modeling as well as developing numerical models for ocean state prediction system along the Indian coast. Professor Rao Garu has been publishing high-quality research papers in highly reputed journals by adding significant contributions to ocean science. Sir, you are proud alumnus of our Andhra University. You are awarded with the Master's degree in Applied Science, Department of Mathematics, Andhra University, and a PhD from IIT Delhi. No doubt to say that your talk boosts the energy levels of many scientists to move further into the field of ocean research. Thank you very much, sir, for delivering very enlightening and useful lecture. Thank you once again, sir. Thank you very much.
Thank you, Naidu Garu. Thank you, Naidu Garu. Thank you, Ramakrishna.
Thank you.
Thank you. Thank you. Bye. Bye.
Thank you, Amani Kodani.